Hey there, students. In this group, we're going to be going over some examples on integration using the use substitution method. Now, the examples we're going to be doing today do not involve composite functions, okay? These are the type of examples you normally see. You have a function like there's an integral of f of x times g of h of x, and you'll be asked to find the integral using use substitution. And use substitution is applicable here if the inner function or the argument of one of the functions, if the derivative of that function is an integer multiple of the other function that has been multiplied by a composite function. So for example, if h prime of x equals an integer multiple of f of x, then we have the green light to use substitution to evaluate this integral. But that's not always the case. Okay, if this were the case, then what you do is you take this inner function and you call it u. All right, so you say let u be h of x, and then you find du. Du is going to be h prime of x dx. But we already determined earlier that h prime of x is an integer multiple of f of x, so it's going to be equal to k times f of x dx. Okay, so if du is equal to k times f of x dx, then we can just isolate f of x dx by dividing both sides by k, and then du over k will be f of x dx, right? And then we'll make a substitution back here. This whole integral, this function, becomes the indefinite integral of g of u. F of x dx is simply going to be du over k. Okay? And then you can then evaluate this one function here as opposed to dealing with multiple functions. All right? This is the kind of problem that you see most times involving integration using use substitution. The examples I'm going to be doing today, this approach will not be applicable to that. All right? So what approach will be applicable? Well, I'm going to have you figure this out while I go over multiple examples. But if you're using this mentality or this approach for these problems, you're not going to be able to find the integral. All right? Okay, now let's start with example number 1. All right, so what is the integral of tan x times the natural logarithm of secant x dx? Okay. All right, what is this? All right, so we know that the derivative of secant x is secant x tan x. We can clearly see that the composite approach is not going to work here. So some people might say, well, let this be u. If you did that, you are not going to be able to evaluate this integral because you're not going to have a multiple of the other function. Okay. So in this case, what if we said let u be, say let u be the natural logarithm of secant x. Okay. So if I differentiate this, do I get a multiple of tan x of the other function tan x? That's the question. All right. So let's go ahead and just differentiate it and see if we end up with a multiple of tan x. Okay. All right. So let's go ahead and differentiate this. We're going to be using the chain rule here. So du is basically going to be 1 over secant 1 over secant x for the outer function times the derivative of the inner function. The derivative of secant x is secant x tan x. Okay, and check this out. You see the secants divide out. So it turns out that du is pretty much tan x dx, which is identical to the other function that we have here, tan x dx. So this is the appropriate du to be selected for this problem. Okay. All right, so let's go ahead and apply the use substitution. So it's going to be the antiderivative. Natural logarithm of secant x will be written as u, and then tan x dx we can replace with du. Okay, so using the power rule for integrals, this is going to become u square over 2 because this is u to the first power plus c. And then we're going to plug back in the value of u. U is a natural logarithm of secant x, so our final answer is going to be the natural logarithm square of the natural logarithm of secant x square, the natural logarithm um, natural logarithm square of secant x over 2 plus c. Okay? Alright, let me rewrite it. I can write it as natural logarithm of secant x like this entire expression square divided by 2 plus c. Okay? So there goes the integral. Okay, let's try another example. Number 2. What is the um, indefinite integral of secant to the third x tan x over 1 plus secant to the third x quantity square dx. Okay? Alright, so now let's take a look at this one. In this case, we have to take a look at this inner function. There's composition actually necessary here. If you take a look at this inner function, if I differentiate this inner function, do I get a multiple of this outer function right here? That's the question. Okay, so let me separate it so that it's obvious what I'm doing. I'm going to separate it as 1 over 1 plus secant to the third x squared, and then times secant to the third x tan x dx. Okay, if I call this inner function u and I differentiate it, do I get a multiple of this, an integer multiple of this piece right here? That's the question, okay? So let's call u 1 plus secant to the third x, okay? So what is du going to be? Du is going to be derivative of 1 is 0. Derivative of secant to the third x, we have to use the chain rule. It's going to be 3 secant squared x for the outer function, which is a cubic function. And then for the inner function, derivative of secant x, let me show you the steps so you don't get confused. Times secant x prime. Okay? That's the inner function. So the u is going to be 3 secant square x. Derivative of secant x is secant x tan x dx. And this whole thing simplifies into du being 3 secant to the third x tan x. So you can clearly see that this is a multiple of that. Okay, so all we just have to do is divide by what that multiple is, and then we can make our substitution. So basically divide both sides by 3. And that's du right there. So du over 3 is going to be, du over 3 is going to be 3 secant to the third x tan x dx. Okay, so now that's what we're going to do. So let's go ahead and apply our u substitution. If we make that u substitution, we're going to have the indefinite integral of 1 over u squared. Okay, and that entire secant third, let me scroll up so you can see what I'm talking about. This entire piece right here becomes 3 du over 3. Okay, so times du over 3. Okay, let's rewrite this integral in a way that's easy to evaluate. I'll factor out that 1/3 there outside, and then times, rewrite this as an exponent, u to the negative 2 du. Okay, so we apply the power rule of integrals. Here we're going to have, this becomes u to the, 1/3 times u to the negative 2 plus 1 is negative 1 over negative 2 plus 1, negative 1. So that equals, so plus c. Don't forget that. Now let's simplify it a little bit more. This becomes negative 1 over 3 u plus c. Okay, so remember what our u was before. U is 1 plus secant to the third x. So we're going to put it back in here. So it's going to be negative 1 over 3 times 1 plus secant to the third x, close that, plus c. Okay, and there goes your integral right there. Okay, all right, let's move on to another example. All right, so for number 3, we want to evaluate the integral of 2x plus 1 over x plus 2 to the fourth times x minus 1 to the fourth dx. Okay? All right, let's take a look at this for a minute. Well, this one looks a little bit weird. So how about we simplify the denominator as much as we can, and then let's see if we can make a use substitution, okay? So how about we do this using the uh, properties of exponents? I can express the denominator, product of powers property, as x plus 2 times x minus 1, that raised to the fourth power, okay, dx. Now, what if we distribute this quantity inside here? What do we get? Let's go ahead and distribute that. So we have the integral of 2x plus 1. And then if I distribute the quantity in the denominator, I'm going to have x squared plus 2x minus x minus 2. Okay, all that raised to the fourth power. And then let's go ahead and combine. So it's going to be the integral of 2x plus 1. In the denominator, you have x squared plus x minus 2 to the fourth. All right, so this looks good. Now, notice, what if I take this u, this argument of this fourth power in the denominator, if I differentiate it, do I get an integer multiple of the numerator? Okay, so let's try that out and see if that's the case. So let u be x squared plus x minus 2. Then du is going to be 2x plus 1. Oh, that's good. dx. That's the integer multiple of the numerator by a factor of 1. So we can go ahead and make that substitution. So we're going to have, we write it as an integral of 1 over u to the fourth. And then 2x plus 1 dx is simply du. Okay, we don't have any integers, any constants to place there. So let's rewrite this for easy integration. We can write this as u to the negative 4 du. Okay. All right, let's use the power property of integrals to evaluate this. This becomes u to the negative 4 plus 1, which is negative 3, over negative 4 plus 1, which is negative 3, plus c. Okay. Okay, let's rewrite this. This is the same thing as negative 1, using the reciprocal property of exponents, u to the third, because of this negative right here, plus c. Now let's put it back in what u was. Okay, u was x squared plus x minus 2. So our final result is going to be negative 1 over 3 times x squared plus x minus 2 to the third power plus c. And there goes your final answer. All right? All right, let's take a look at another example. Question number 4. Let's see, what if we want to find the integral of secant square x tan x over 4 plus tan square x dx. Okay? All right, so we've got to be careful here. Take a look at this to see what should be the appropriate u selection. Okay? If I take the denominator as a whole, that might sound like a smart choice because this 4 is going to drop off. And if we differentiate tan square x, we might end up with an integer multiple of the numerator and the x. So let's try that out. If I pick the numerator, for example, it will be complicated. It won't work out at all. So let u be 4 plus tan square x. All right. So du is going to be the derivative of 4 is 0. If we use the chain rule here for the quadratic outer function, that's going to be 2 tan x times tan x prime. Okay? So derivative of the outer times the derivative of the inner. So if we differentiate the inner function, du is going to be 2 tan x. Derivative of tan x is secant square x. Okay, secant square x dx. So that's du. So is this an integer multiple of the numerator function? Absolutely. Okay, if you multiply the numerator function by 2, you get this right here. So this is exactly what we like. So what we're going to do is divide both sides by 2 so that we can have a clean substitution of tan x secant square x dx. So if we divide by 2, we're going to have du over 2 equals tan x secant square x dx. Now we're ready to make our substitution. Okay. All right. So let's go ahead and do the substitution. Let me do it on the side here so that you can see it, see what's happening without getting confused. Partition my workspace. Okay, now let's see. U goes on the bottom, so this is going to be the integral of uh, 1 over u, since using the denominator, and then this entire numerator on dx will replace with du over 2, okay, because that's what tan times secant square x dx is. You know that multiplication commutes, so the order with which you write this doesn't really matter, okay? All right, so du time 1 over u times du over 2. All right, so let's rewrite this. This is going to be 1/2 times the indefinite integral of 1 over u du. No need to rewrite this because we know what the integral of this is. This is going to be 1/2, and integral of 1 over u is a natural logarithm of the absolute value of u plus c. Okay? All right, so this is going to be 1/2 to the natural logarithm absolute value of u. We know that u is 4 plus tan square x, so we can put that here, 4 plus tan square x plus that plus c, and there goes your final answer. Okay, so that's that for the indefinite integral of this expression right here. Okay, let's take a look at our last example, question number 39. Oh, I'm sorry, question number 5. Question 5. Okay, so question 5, we want to find the indefinite integral of 2x plus 5 over 2x minus 3. Okay? All right. Now, whenever you have functions like this, it's always advisable to decompose this function. This is a very easy function to decompose. You can use long division. If you use long division, you find out that this divided by this is going to be 1 remainder 8. But there's an easier way to do this without using long division. You can ask yourself, how can I express this number as a combination of -3 and another integer? Okay? How can we do that? That's the question. So I'm going to write this as 2x over 2x minus 3. Now, 5 is the same thing as -3 plus 8. So replace this 5 with -3 plus 8 dx. Now, why did I do that? Well, check this out. I can express this as the integral of 2x minus 3 over 2x minus 3 plus 8 over 2x minus 3. Guess what I just did? This is long division. I'm just doing it a different way. This is exactly what long division is. If I wanted to divide these two using long division, this is how it's going to turn out. Okay, so if I finish this up, this is going to become the integral of 1 over 2x. I'm sorry. Integral of 1. If you divide these two, you're going to just get 1, right? Of 1 plus 8 over 2x minus 3 dx. Okay? All right, so this is long division. All right, so let me show you what I'm talking about when I say it's long division so you can understand what I'm doing here. So if you wanted to do this using long division, the top goes in here. So this is old-fashioned long division, okay? What you learned in algebra 2. 2x plus 5 on the top goes here. 2x minus 3 goes out here. Okay, so let's divide this. All right, so how do we divide this? 2x goes into 2x once. 1 times 2x is 2x minus 3. And then you just simply subtract, right? When you subtract, this becomes a minus, this becomes a minus, that becomes a plus. So this is going to be 8. Okay, so your answer is going to be 1 plus 8 over 2x minus 3. Guess what? That's exactly what we have here. I just used a different way of doing it. Okay, so this method I use is a little bit too abstract for you. You can just use long division to simplify this expression. All right. Okay. All right. So there you have it. Now, what we're going to do next, we are going to break evaluate this integral using term by term integration. Okay, so this is going to be the indefinite integral of 1 dx plus the indefinite integral. Let's factor out this 8 of 8 over 1, 8 times the integral of 1 over 2x minus 3 dx. Okay? Alright, now, integral of 1, piece of cake, we know that that's just simply, x. But this one is not that easy, though. So this is going to be x plus. Now, for this piece right here, we might have to do some kind of use substitution. If I differentiate this denominator, do I get an integer multiple of 1 is the question. Okay? So for this piece, let's do this on the side. What if u were 2x minus 3? What is du going to be? Du is going to be 2 dx. Okay? Oh, wait. 2 is a multiple of 1. 1 times 2 is 2. Okay, so that's perfect. That's what we want. So if we divide both sides by 2, we'll find out that du over 2 is simply 1 times dx. 1 dx, or dx makes no difference. Okay? So I can use the u substitution here, and I can express this as 8 times 1 over u. Okay, 1 dx is going to be du over 2. All right? So now let's simplify this further. I'll rewrite it so I can integrate with ease. Okay, 8 plus 8 times the integral, first 8 over 2, is 2 down here. 1 over u I can leave like that, du. Okay, so this becomes x plus 4. The integral of 1 over u is the natural logarithm of the absolute value of u plus c. Okay? Alright, so let's do our substitution back. We said u is 2x minus 3, right? So let's put that back in. So this is going to become x plus 4 times the natural logarithm of the absolute value of 2x minus 3 plus c. And there goes your final answer. Alright, so that's that. So thanks so much for taking the time to watch this presentation. Feel free to subscribe to my channel by clicking up here. Please post the comments to let me know what you think about this clip. More clips come from mygoserve.com. Thanks again and have a wonderful day.